Here we're going to introduce the indefinite integral. And the definite integral and the indefinite integral have similar notation, but they're actually very different. The definite integral we saw is a number, often corresponding to the area between a curve and the x-axis, the net area. But the indefinite integral does not represent a number, it represents a family of functions that have a certain derivative. And it's only that the fundamental theorem made the connection between antiderivatives and definite integrals that we use the same notation, but really they're completely different things. So to define the indefinite integral, notationally we use the same integral sign as though we were going to write a definite integral. And then what we do is we put in a function, and then the differential. So this is called the indefinite integral with respect to x. And what it represents is the family of functions whose derivative is f of x. So if we let f of x be any function whose derivative is lowercase f, then what we would say is that this indefinite integral is equal to uppercase f plus c. That c is the constant of integration, and that's because if capital F, its derivative is lowercase f, then obviously capital F plus 2 and plus 7 and plus a million all are going to have the same, are all going to have derivative of lowercase f, and that's because the derivative of a constant is 0. That's called the constant of integration. So you want to make sure you don't forget to do that whenever you're doing indefinite integrals. Alright, so let's do one example here. One that's straightforward, doesn't require any techniques or anything. So this this problem here, it says evaluate the integral of 2x cubed plus cosine of x. Again, notice it's an indefinite integral because there are no values in the upper and lower limits of integration. So we know we're just going to be writing a function. So you can take it term by term, the antiderivative of 2x cubed. Well, let's see. The way I think about it is I know that the antiderivative should have an exponent 1 more. And then what would happen is I would take this 4 down, right? And then I would diminish the power if I was taking a derivative. But in this case, I have a 2 here. So what would the 4 have to multiply by to get a 2? That would have to be a 1/2. And you can always check, of course, to make sure that this guy's derivative ends up giving you 2x cubed. The antiderivative of cosine of x, this is just where you bring your knowledge into the problem. The antiderivative is just sine of x. And then I got to add the plus c because this whole family of functions has this derivative inside, this derivative 2x cubed plus cosine of x. So there's the definition of the indefinite integral. What we'll be doing over the next couple of lessons or videos or so is looking at some techniques to evaluate indefinite integrals. There are a couple of ones that you'll be responsible for. I'm sure there are books on techniques of finding and evaluating indefinite integrals, but for us we just need to know a couple of basic techniques that'll get us through the majority of the problems we'll come across. The first technique for evaluating indefinite integrals, or in other words finding antiderivatives, is called the method of substitution. Now, substitution in general, as a mathematical strategy, what it tends to do is it turns problems that look more complicated than they actually are at heart into ones that are more manageable. So I'm just going to note that all we're going to do here is we're going to turn an unfamiliar integral into a more manageable one, or into one we can handle. This is something you probably do or have done in your prior mathematical experience. If I guess I'm just going to note down at the bottom here. Like if I gave you something like in trigonometry, sine of squared x plus 2 cosine of x plus 1 equals 0. Sorry, 2, I meant this to be a sine. 2 sine of x plus 1 equals 0. That may look like an intimidating problem until you say something like, well, let's just let my u be sine of x. And then this problem becomes u squared plus 2u plus 1 equals 0. And then you can see that you would just factor it. And it's just u plus 1 times u plus 1, which means u equals -1, which means that sine equals -1, right? Which means x equals 3 pi over 2 if we're going on the interval 0 to 2 pi. So that, I mean, that's just a quick example of how substitution can make a problem that kind of looks more difficult than it is into one that we recognize. So the first few examples I'm going to do don't necessarily require substitution, but they're good places to start just so you can see how the method works. So let's say you're doing the integral, the indefinite integral sine of 2x. You don't know off the top of your head the antiderivative of sine of 2x, or that 2x is just bothering you. What you can do is replace that 2x with a variable u. So I'm going to say let u be 2x. And that's going to take care of this 2x. It's important that we also replace the differential. And the way we do that is we just take the derivative of both sides of this equation, u equals 2x. So the derivative of u, we're going to use the differential du. The derivative of 2x is 2 dx. And now we make a full substitution. So this is going to be now sine of u. Dx also needs to be replaced with the differential du. So if du is 2 dx, that must mean that du over 2 is equal to dx. So I can replace the dx with du over 2. What I like to do is I put the du here, and then the divided by 2, I usually write that as 1/2 outside the integral. Constants can come out. So now I know the antiderivative of sine of u, or of sine of anything, so that's negative cosine. So it's negative cosine of u plus c. And we're pretty much done. The only thing is this problem was originally in terms of x, so I got to go back and make that substitution back. I got to put the 2x in for the u. Right, and there's our answer. So, I mean, some of you might have been able to grind through that without the u substitution, but you may notice that it'll work. It'll turn one that's a little more complicated into one that's a little easier. Let's try another example. Let's say we've got the integral of 4x plus 7 to the 5th. Notice you, of course, could just multiply that out 5 times or expand that out and then go term by term, but that's not going to be practical, especially if the 5 is like a 50. But you do know the antiderivative of something to the 5th. So I'm going to let my u be that whole inside, 4x plus 7. And that means that du is 4 dx. And so now I'm going to turn this integral into u to the 5th. And my dx is really du divided by 4. So I'm going to put the du here and the divided by 4, the 1/4 out here. So this equals a 4th, and the antiderivative of u to the 5th is going to be u to the 6th times a 6th plus c. So that's 1 over 24 u to the 6th plus c, but we have to replace the u with the 4x plus 7. So that ends up being 4x plus 7, and ends up being 1 over 24 times 4x plus 7. to the 5th plus c. Notice you can always check, sorry, to the 6th. I'm messing up left and right here, to the 6th. Notice you can always check by taking the derivative of this guy. If you take the derivative, the 6 comes down. 6 over 24 is a 4th, times 4x plus 7 to the 5th, but then times by using the chain rule, you'd be timesing by that 4 on the inside, which would kill the 4, that 1/4 in the front, and you would have exactly what we have here. So those are two very basic substitution problems, but those are good to start with. In the next few videos, I'll give you a few more examples of ones that gradually get more complicated.